You saw me stop when I saw them and I was like, what the hell are they doing?
Yeah, you were like wondering what they were.
Okay, so what we're going to look at here, we've got some properties of polar form. So if we have two complex numbers in polar form multiplied by one another, then we can add the angles. If we have one complex number divided by another, then it's the top one take away the bottom one. You can think of these, they're quite similar to the laws of logarithms, aren't they? It's a way of collecting logarithms. And the last one here, plus k2 pi just insinuates, well, if we've got a periodic revolution, then it's going to repeat itself. That's what the k2 pi is for. Okay, so here, like the first thing I'm going to do is just show you that we can write order of multiplication doesn't really matter, does it? So we can write it like this, all right, and then we can perform the 2 times 3 will be 6, and cis of pi on 4 times cis of pi on 2. We're going to use the first rule here to collect them. 6 cis of pi on 4 plus pi on 2, which will take us to 3 pi on 4. Okay, so in a moment I'll show you a few calculator skills, but you can just type that into your calculator and it will spit this out as well. And we can convert that to Cartesian form by making it 6 cos of 3 pi on 4, 6 sine of 3 pi on 4 times pi. Alright, let's move on to this one here. We have 2 cis to the power of 3 theta. Now what this means is it means 2 times, and then we have cis theta times cis theta times cis theta, okay? That's what to the power of 3 means, doesn't it? Times itself 3 times, all on top of cis of minus theta. So at the top, if we're looking at this, you know, if I have cis theta times cis phi, I'm going to add those powers, add those together. So that's going to become cis 2 theta, cis 3 theta. And so we've sort of derived a rule there, and I'll add that up here because it's not articulated clearly. But if we have cis of n theta, or cis to the power of n theta, that's equal to cis of n theta. And that's just derived from the multiplication rule. Okay, then we have cis 3 theta at the top and cis of minus theta at the bottom. So now we're going to apply this one, where we have the top power take away the bottom power. Not power, angle. 2 cis of 3 theta take away negative theta. 2 cis of 4 theta. We can't express that in Cartesian form because we're not given the size of an angle. Okay, good. So that's that question there. Flick over the page. We've got question 2 here. And I think what I'll do, I've written everything up already, so I'll just talk about it and then you guys can copy it down. So we have some complex number, r cis theta. You can think of it as like a plus bi. And so here it is, I've sketched it here on the argand plane. Okay, it wants us to find z conjugate minus z and minus z conjugate in polar form. So firstly, let's talk about z conjugate. So if I have a plus bi, the conjugate is going to be a take bi, right? The conjugate is just the reflection in the real axis. This is the conjugate of z. So if I'm trying to sketch this, all right, this angle here is going to be minus theta. There we've got minus theta down. And if you think about r cis of minus theta, I'll just show you why it's true. We have r cos of minus theta plus I sine of minus theta. And cos of minus theta is cos of theta. This is one of the trig identities we've explored last year. All right, not something you expected to know, but written on your trig formula sheets there and so forth. But I sine of minus theta remains. And so that shows you that the real component has a positive angle, all right, doesn't change its value, but the sine does have the negative. All right, we're going in that negative direction. Okay, so the conjugate of z is r cis of minus theta. Okay, then we have negative z. Okay, how are we going to express that in polar form? Well, firstly, if this is z, think about vectors. If this is z, it has direction. Negative z is going to be the opposite direction. So all we're doing is flipping it in the opposite direction. That's negative z there. So we can describe it like that as negative r cis theta, and that's correct. What it would mean, if this angle is theta, it means this angle is going to be theta. Okay? Now, from here, the whole way around to there, that's an angle of negative pi. All All right, that whole thing is negative pi. I might clear a bit of space so I can make the argument. This whole thing would be minus pi the whole way. And so if we want to describe this complex number, negative z, it's going to be minus pi plus theta. Minus pi plus theta, which is the same as theta take away pi. Okay, so we can describe it like that, or we can describe it like this. And lastly, we have negative z conjugate. So again, I'd make the argument like this. I'd go, this is the conjugate of z. So we make the vector argument. So negative z conjugate is in the opposite direction. All right, so this angle has a size of theta. The whole way around is pi, which means the angle to here is going to be pi, take away that theta. All right, so we can describe it like that or like that. Okay, so we're asked to find them in polar form. So this can be like a useful way for you to find any z conjugate minus z or minus z conjugate. All right, that's like the general form of it for any angle and for any modulus. And one more thing is, it says describe its relationship to z. How do we map from z to z conjugate? Well, z to z conjugate is just a reflection in the real axes. Z to minus z is a rotation of pi units about the origin. It doesn't matter in which direction we rotate it. We can go pi units that way or pi units that way. We'll end up in the same spot. And the last one, minus z conjugate, is just the complex number z reflected in the imaginary axis. Okay, that's question 2 there. That's enough to do C2. I will just take you through a few calculator skills. So if you can pull your calcs out, your weapons of math destruction.
Yeah, right, 6.
This one's mine, isn't it? Okay, so it's not heaps neat, your calculator. But let's say we've got a complex number. We'll go to option and complex again. Option complex. And I want you to then press the across arrow. And it's going to bring up these options. We've got the real part, the imaginary part. And then you'll see for F3 and F4, you've got an arrow that says R angle theta. All right, what do you think that might mean? Modulus argument, okay? So let's put in a complex number, like one we had before was in question 1C, was 3 plus 3i. So let's type in this complex number, 3 plus 3i, and then we'll press, now convert that to polar form, evaluate. All right. So if I press this, type that in, and then I'll press that button, I've got 3 root 2, which is the same as the square root of 18. And I've got angle pi on 4, angle 1 on 4 pi, which is the same as 3 root 2 cis of pi on 4. Okay, and you can go back the other way as well. So we've gone from a Cartesian form to polar form. And we can use F4 to go the other way. I can take that complex number and say, put it in Cartesian form for me, and it will bring it up as well. Okay, so you can use both of those to convert between the two. All right, is that pretty clear?